Okay, thank you, and obviously thank you to the organizers for allowing me some time to talk about my research project. So I'll begin by just reminding you of the basic objects that probably need no reminding, but I'll do it anyway. So you have your compact Riemann surface with genus at least two. You have your moduli of vector bundles over the surface, and you have your moduli of, I will consider just SL and C Higgs bundles over your surface, which inherits a natural symplectic structure from the fact that you can put the cotangent of the moduli of bundles as an open dense set inside it. Okay, so now you have a symplectic manifold. You want to find some Lagrangians, right? One idea you can try is to first take one already known Lagrangian, some subvariety inside it, and consider its conormal bundle. For very simple cases, that works. So if you take a point inside a moduli of vector bundles, the conormal fiber, the conormal bundle is just a cotangent fiber, which is obviously Lagrangian. But for more complicated cases, it doesn't really work. So you try the next best thing, which is you try to find some Lagrangian, which agrees infinitesimally in your submanifold with the conormal bundle. Okay, so just some reminders on the C star action, which should be important for the construction. So you have your natural C star action acting by scaling the Higgs field, and the point is that at a fixed point of this action, everything decomposes. So the bundle itself decomposes into a direct sum. Your field goes from one summand to the next. Your tangent space also decomposes into some weights. The same with your endomorphism bundle. So to do our conormal construction, we're going to consider our Lagrangian will be a component of the nilpotent cone, where H is just the usual Hitchin map. And inside it, you have a component of the fixed point locus. So you compute the conormal, and via this sequence, you replace everything with the correct weight. So the nilpotent cone has weights less than or equal to 0. Your fixed point component has weights 0. Use the fact that when you dualize, you exchange weight j with 1 minus j. So your conormal space will have weights bigger than or equal to 2, but now you also have to account for your variation along the fixed point locus. So you have to add weight 0 as well. So how do you build such a thing? Well, you consider a somewhat related object, the upper flows of a fixed point, which are just all the points whose C star limit to 0 is a particular fixed point. And this at the fixed point, its weights at the tangent space are all of the positive weights. So there's this BB slice that was considered by Collier and Wentworth, which essentially you are considering some harmonic representatives, and via this slice they were able to show that this is a global parameterization for the upper flow, and via using that they were able to show that it is Lagrangian. So now what we did is we sort of tinkered with this slice in order for it to have the weights that we wanted to have. So you get like a piece of Lagrangian around your fixed point, But the issue is that now a priori you don't get these global slices anymore. So you need to find, okay, how are we going to glue these local things? Okay, so you're going to consider an entire fixed point component, and the collection of all the upward flows, also sometimes called the attractor. So everything that flows to that particular fixed point component, and you're going to keep track of each point as it reaches its limit via this curve. Okay, so and if you use the coordinates given by those slices, you can show that being in that slice is precisely equivalent to your point arriving at the limit with velocity 0. And this sort of zero velocity condition that will define globally our Lagrangian. Okay, so and so this is just the result telling us that such an object exists. Okay, so just to give a cartoon, so you have your upward flow at a single point with all positive weights, but in order to go to our object, you swap weight 1 with weight 0, and you now get something which is smaller in the upward direction, but moves along the fixed point locus. Okay, so for rank 2, this actually gives an already known object. So if you take a fixed point, it's of this type. And if you want to add you have to add just weight 2, right? So you don't want weight 1. That's what characterizes the Lagrangian. So the only thing you do is you add something in the upper triangular corner there. And these are precisely Higgs bundles for the real group SL2R. So these Lagrangian will be components of that moduli space. And in particular, for top degree, you recover the Hitchin sections. Okay, so for example, by mirror symmetry considerations, it is interesting to know how these Lagrangians interact with the Hitchin vibration. Namely, how is the intersection with the general fiber? So we're going to fix a point in the Hitchin base, or essentially we are fixing a characteristic polynomial. And we are going to fix a fixed point component by essentially prescribing the degrees of the phi i's. If you remember, these are just the restrictions of the field to each of the sum ends of the fixed point. So for rank 2, it is actually quite. There is this result by Laura Shaposnik, where she proved that the intersection of each component with a regular fiber is non-empty. But in fact, if you go to the proof of that theorem, it's not so hard to actually get the number of intersections. Essentially, if you are fixing the determinant, you just pick some of those zeros, some of the zeros of the determinant to go to gamma, and obviously the rest of the zeros have to go to beta, and then there's this 2 to the 2g, which accounts for the choice of the line bundle. Okay, so in general, so this might seem a bit silly, but we're going to sort of split our problem into 2 components, one horizontal and one vertical. So we're going to try and decompose our Lagrangian into each of its fibers and try to find out the intersection with each one. So we first have a bit of an horizontal problem. So we want to find out for which fixed points there is the intersections in the sort of zero velocity upward flow exists. And then given one of those fixed points, we want the vertical problem. So we want to know how many intersection points there are. So with this cartoon, I think it's more or less simple to understand. So you have a bunch of intersection points which flow to some fixed points. So first we try to find out which fixed points these are, because then you know that you only need to focus on these ones if you actually want to compute the intersections. Okay, so how do you find out these fixed points? So you take a Higgs field in our Lagrangian, looks like this. So these zeros are to account for the removal of the first of the weight one direction. But if you are in a zero of one of your phi i's, you have this invariant subspace, right? And so you notice that everything here has trace zero, right? The full matrix and also your invariant matrix. So at this point, the characteristic polynomial, which has trace zero, right? There's no n-1 term, must decompose into two other smaller degree polynomials with the same property. So with no i-1 and with no n-i-1 parts. Well, this is not always possible. So this gives rise to a certain system of polynomial equations if you equate the equal degree parts. And this system is only solvable if a certain polynomial in your A's is zero. And so there are some easy observations you can do about this polynomial. For example, it is symmetric. So the polynomial for ni is the same for n and n-i. For I equals 1, it will be the determinant. And then these you can compute, and you find out that well, for 4-2, this is still very simple, right? It's A3, but from 5 onwards, the polynomial starts to get quite complicated. But if you organize the weighted degrees of these polynomials, and by that I mean that, for example, A3 as weight 3, A4 as weight 4, and so on, you start to get almost a very familiar object, right? So you get Pascal's triangle, except with these deficiencies here in the middle, where the numbers are half of what they should be. So, but assuming this pattern holds, which we know it does, if you can also show that for generic A, these sections here have reduced divisor, and the divisors are this joint. So, for example, 6-2 and 6-3, I want them to have reduced divisors and also no common zeros. So this is what this means, and this was actually proven for n odd just yesterday. You can actually give a formula for the number of fixed points, provided you impose the condition that they are very stable, which essentially means that your phi i's only have simple zeros and also don't have any zeros in common. So you get this formula, which is essentially are distributing the zeros of the Rn i's to phi I and to phi n minus I, and this again is a factor that accounts for the choice of line bundle. Okay, so that takes care of the horizontal problem. So now we want to see how to take care of the vertical problem. This is made quite easy because I am in a very stable fixed point. And we actually have this result by Hausel and Hitchin, which counts the intersection points with the entire upward flow. So I'll try to make it quick, but essentially to each intersection point corresponds, to each intersection point corresponds a certain choice of eigenvalues over each zero of these phi i's. So over each phi I, generally your spectral curve would be unramified. So you have to pick n minus I zeros, n minus I eigenvalues. And to each choice of those eigenvalues corresponds an intersection point. And with that, with some easy combinatorics, you can find out the full intersection number. But what happens in the Lagrangian? So the whole point is to find out which of these choices of eigenvalues can give you a point in the Lagrangian. So if you take a look at the point in the Lagrangian, if you are in a 0 of phi 1, you have this invariant subspace where the Higgs field is just 0. So you have to pick the other ones. You have to pick the two non-zero eigenvalues. And if you are in a 0 of phi 2, you also get this invariant subspace, but here in the quotient, you have to pick the 0 eigenvalue. So the point is, while for the entire upward flow, you can pick any two of these three pre-images, to be in the Lagrangian, you are actually forced to pick the two non-zero points. And the same here for phi 2. So any one of these three pre-images would give you a point in the upward flow, but to be in the Lagrangian, you are forced to pick the 0 eigenvalue. And so this gives you the count. So this might seem a bit silly. So this part here is the number of fixed points. And then since you only have one choice for each 0 of your phi 1 and for each 0 of your phi 2, you actually don't need anything else. So this is 1 to the m1. So this is just 1. I just wrote this so you can compare it better with the formula by Hausel and Hitchin. Okay. Yeah, and so also, but this, what I described to you gives only necessary conditions, right? So I started with an intersection point and I tried to find out, and all I did was derive some necessary conditions. And this is just a bound, right? But the machinery of Hausel and Hitchin, well, how do they go from the choices of eigenvalues to the intersection point? They start with the Hitchin section and they perform successive Hackett transformations at the zeros of your field in order to reach the correct fixed point. And it turns out that the same strategy also works here. So I'll give you, maybe I still have some 10 seconds. So there is a certain diagram that you have to check that commutes, but essentially everything works as it should, which is very nice. And so it shows the result for n odd. And that's it. Thank you.
Okay, so questions, comments?
All right, so the assumption here, well, I guess I have two quick questions. One is, what's the main difference between the even and odd case? Assuming, I guess all your bundles were line bundles in this case. So what goes wrong in the even?
What's wrong in the even case? Yes, in the even case, what's wrong is precisely these deficiencies here. So there are some tools that. So we understood more or less how these polynomials arise. But there is a certain additional complication that shows up in the even case that we haven't quite been able to sort out. But I mean, I am pretty confident that it will work, but there's still some additional work to be done. And also in the even case, so there's that for the polynomials, and then in the even case, that there's also, so if you think that there are now 4 pre-images, there will actually be 2 choices, because you can pick, if you had like an extra pre-image here, you could actually pick either this one, or you could pick this one, or the complementary choice. So there will be two choices. So it's a bit of a funny phenomenon because there's a 2 that disappears on one side but reappears on another side. But yeah, there are still some details that are stopping us from calling it a theorem for an even.
Thanks.
Any more questions? No? Okay, so let's thank Rodrigo again. So we should start at 11, so 5 minutes. So the next speaker.